Hi and welcome back. Today we're going to look at the electrochemical series and how we can calculate the potential difference for this and apply it to galvanic cells so we know the voltage that the cell will produce, what our anode and what our cathode is. So let's get started. So the potential difference when we talk about a cell is all about the difference between the two half cells, their different reaction potential. Okay, so one half cell will have a greater tendency to push electrons into the external circuit than the other, causing the current to be generated. This is of course going to be our anode, i.e. it will be the strongest reductant. It will be oxidized because it wants to push those electrons away. So the potential difference exists between the two cells in this tendency to generate electrons and push them into the circuit. This is also referred to as the electromotive force, or EMF, that you may have seen or heard mentioned in physics. It's measured in volts, so anytime we're measuring the voltage of a battery or something like this, what we're actually doing is giving a value to the potential difference between the two cells. We measure it using a voltmeter, and it measures the amount of energy supplied by a fixed amount of charge flowing from the galvanic cell, okay? So remembering that the surface area of the electrode needs to be in contact with the electrolyte, and those reaction conditions will limit or increase the amount of electrons that can be passed through our cell at any one point in time. The standard half-cell potentials of the electrochemical series can give us an indication of the cell voltage. Remember the numbers that are listed down the right-hand side of our electrochemical series? That is what we're going to use in order to calculate our cell voltage. So looking at the standard half-cell potentials, i.e. the values on the right-hand side, these are a numerical measure of how likely the half cell is to have a reduction reaction. So the more positive the value, the more likely the forward reaction on the electrochemical series will occur. So reduction is more likely to occur when it has a high E0 value. So something like fluorine, which has a high value of positive 2.87, is going to be reduced. It's very unlikely to be oxidized. Whereas something like lithium, going lithium plus to lithium solid, lithium is a very reactive metal, lithium solid. It doesn't want to gain electrons. It's more stable as lithium plus. It's very good at giving its electrons away, i.e. it is very good at being oxidized. It's a strong reductant, and we see that as a result it has a corresponding negative 3.05 E0 value. So the potential difference of a cell at SLC, remembering this is 298 Kelvin, 1 atmosphere of pressure and 1 molar solutions, is literally the difference between the E0 of the two half cells. So our E0, okay, or the potential difference of the cell is going to, so E0 of the cell is equal to the higher half cell, so the more positive one, minus the lower half cell, which means this will usually be a smaller positive value or highly likely a negative value, which means that when we minus a negative, we end up with a positive. If the cell generates power, i.e. it is generating electrical energy from a spontaneous reaction, then our E0 for the cell will be positive. If our E0 for the cell is negative, that is a non-spontaneous reaction and it would require energy to make that reaction occur. Okay, so all our galvanic cells must be set up where we have a positive E0 value. So we have a look at some of these questions and how they would appear. Let's have a look at a cell made from silver ions. So silver ions and silver solid, and Fe2 plus and Fe solid under standard conditions. This is just telling me that the electrochemical series should apply. We want to predict the overall cell reaction, identify the anode and the cathode, and determine the direction of electron flow. Okay, so we talked about predicting reactions in our last video. I'm going to circle what I have present. So I have Ag plus and Ag solid present in my cell. I have Fe2 plus, which I'm going to find down here, and Fe solid. Be careful with your ions because with iron, there is Fe3+ listed in your electrochemical series as well. So you can see here Fe3+ to Fe2+. You've just got to make sure you get the right combination, and this one specifies Fe2+ and Fe solid. From this, remember, we're looking for the negative gradient, and we can see that that will occur between silver plus and Fe solid. So my reactions will go this way. So the reduction reaction is going to be Ag plus to Ag solid, and the oxidation reaction is going to be Fe solid to Fe2+. So if I'm going to draw my electrochemical cell for that, by convention we often put the anode on the left-hand side. So anode, remember, an, oil, rig, cat, or red cat. So reduction occurs at the cathode, which is positive in a galvanic cell. Oxidation at the anode, which is negative in a galvanic cell. We said the oxidation is going to be Fe solid. So this is Fe solid and Fe2+ in solution. I'm going to have Ag solid, Ag plus in solution. I'm going to connect them with my salt bridge, an external circuit with my voltmeter. And this will be the anode, so I will have Fe solid going to Fe2+ plus 2 electrons. And at my cathode, I will have Ag plus an electron going to Ag solid. It also wants us to predict the overall cell reaction and the electron flow. The electrons will flow from the source where they're produced, so from the anode to the cathode. We show that with arrows through the wire and just indicate that it's our electrons that are moving. The overall cell reaction, I can see I need to multiply this one by 2. So overall, I will have Fe solid plus 2 Ag plus aqueous goes to 2 Ag solid plus Fe2+ aqueous. The oxidant in this case is the silver plus, and the reductant in this case is the Fe solid. Okay, and we can see here that the reductant here, the strongest reductant is the one that is lowest on the right hand side, and that is indeed Fe solid. The strongest oxidant is the one highest on the left hand side, which is indeed Ag plus. You can practice some more of these types of questions in your textbook on page 138, questions 1 to 5, looking at predicting which will be which. If we were to work out the E0 for the cell, you may remember we said it was the higher one, so we take this value here, plus 0.80, minus the lower one, so we're going to minus 0.44. So we will end up with a positive 1.24 volts would be what we would expect to produce from that cell. So as you saw when we're drawing a galvanic cell, we need to make our diagrams clear. We must indicate the voltmeter within the external circuit. We have the external circuit, which is the wire that connects them. We show the direction of the electrons moving from anode to cathode. The electrodes must sit within the electrolyte solution, as must the salt bridge. We indicate the solid or the material of the electrode and the ions that are present in the electrolyte. So this zinc half cell is made from ZnSO4. Okay, and this copper half cell is made from CuSO4. This would be our cathode, this would be our anode. When a question asks us to show the polarity of the electrodes, what it's asking us to do is indicate which one is positive and which one is negative, which, remembering, in a galvanic cell, cathode, cations positive, anode, anions negative. So if we put that all together, we can look at this question. It's asking us to draw a labeled diagram of a cell formed from chlorine and chloride, Sn2+ and Sn solid. and then use the electrochemical series to indicate the half-cell reactions, the anode and the cathode, the direction of electrode flow, the polarities, remembering that indicates which is positive and which is negative, the overall reaction, and the cell potential difference. So, if you have a look at that, you're going to find chlorine and chloride on your electrochemical series, which is going to be right up near the top. It's the fourth one down. This is our Cl2 to Cl minus reaction, and then the Sn2 plus to Sn solid is further down. So using our electrochemical series to predict, we are going to see the reaction between chlorine gas and Sn solid. So chlorine gas will be reduced to chloride, Sn solid will be oxidized to Sn2 plus. Remembering chlorine will be bubbled through a gaseous electrode. This will be the anode, this will be the cathode. The lower one is the anode. And then, so this will be the negative, this will be the positive. When we draw that out, this is what we would see. We have the chlorine gas being pumped through a gaseous electrode, which will usually have a platinum cathode, will be positive. We will have chlorine going to chloride in that half cell, Sn solid going to Sn2 plus in the opposing half cell. The anode will be the negative electrodes, therefore drawn this way, the electrons will move to the cathode, right from left, and our salt bridge. Remembering ions from the salt bridge, the anions will go from the salt bridge to the anode, and the cations will go from the salt bridge to the cathode. The overall reaction is going to be Cl2 plus Sn solid goes to 2Cl minus and Sn2 plus. And it also asked us to find the E0 of the cell. So we're going to take the E0 value for chlorine, which is positive 1.36, and we're going to subtract the E0 value for tin, which is negative 0.14. So we're going to add 0.14, so that will be 30, 40, so it's going to be positive 1.5 volts would be the voltage we would expect to see from this cell. So that's how we go about using electrochemical series to determine voltage. There is a couple of things that we need to note in terms of limitations. The electrochemical series only holds true under standard conditions. If we're working with very concentrated solutions or at different temperatures, we can see variation in the sequence of the electrochemical series. Watch out for this in questions, because they sometimes will ask if you would expect to see a variation, or look to see if they're using concentrated solutions like 6 molar or things like that, because then the reactions may not be as predicted. Outside of SLC, the half-cell potentials can vary. That means the voltage can change, altering the position of some species in the series. The electrochemical series states whether or not a reaction, we can use it to predict whether or not a reaction will occur, i.e. will it be spontaneous, but it gives us no indication of the rate. So it may be something that occurs very slowly that we can't observe within the timescale of watching the reaction. Or it may occur very quickly. The electrochemical series only states that the reaction should occur, not how quickly that reaction would occur. Okay, so that's very important as we move on in terms of we can predict whether or not it will, but it may not be suitable for the production of a battery or something like that, because the reaction may occur very slowly at standard conditions. I'm going to leave you with this VCAR exam question to have a look at, and then the solution is on the next slide. So have a look. What you're doing here is the switch here is just basically saying when the two electrodes are connected together, i.e. it facilitates the formation of the spontaneous reaction if it's going to occur. Note that you have Fe2 plus and Fe3 plus in here with inert electrode, so that platinum is not going to be part of the reaction. The other one is a copper and copper 2 plus. Use your electrochemical series to answer the multiple choice question and then check your answer. Okay, hopefully what you came up with was answer C. You can see here that 60% is generally on average for these redox kind of questions. They are answered not very strongly across the state, but they always do turn up on the exam. There's always a lot of redox on the exam. So if you can get on top of these, you're going to be starting to improve your rankings and have a solid understanding of a good portion of what will be on your exam. With this one, we need to look at the two half cells. We have Fe3 plus to Fe2 plus. Remember, I pointed that out earlier. Copper 2 plus going to copper solid. Because the Fe3 plus is above copper, copper will undergo the oxidation reaction, whereas Fe3 plus will be reduced to Fe2 plus. So the electrons will flow from the oxidation, the anode, copper, through to the platinum electrode. We will have 0.77 minus 0.34, and you can see that this cell would produce less than 1 volt of energy. Hopefully you're feeling okay with that. Remember to check in with me and let me know if you have any concerns and you've got extra questions to work through in your work packet. Good luck, and I'll see you in class.